Hi, this is Adam Lehman from Hamilton County Conservation District in Ohio. The following video is from part 4 of a 4-part day-long workshop on estimating pollutant loads using the U.S. Environmental Protection Agency's Pollutant Load Estimation Tool, or PLET. The workshop was designed to assist natural resource managers with estimating load reductions for conservation projects, as is often required by important funding sources. Video from other parts of the workshop can be accessed from the Hamilton County Conservation District's YouTube channel. A link to that playlist is provided in the description of this video. Part 1 of the workshop covered the context of why tracking pollutant loads and their reductions is important and the status of those efforts nationally and in the state of Ohio. Part 2 of the workshop covered an introduction and a detailed walkthrough US EPA's new pollutant load estimation tool, or PLET. Part 3 was an overview of the methods and parameters used by PLET and resources for estimating those parameters. And Part 4 was a GIS and spreadsheet workflow demonstration for how to generate the needed parameters for an example agricultural treatment wetland project. Also linked in the description is a resources web page that was associated with the workshop. This web page contains lots of linked and downloadable resources discussed throughout the workshop. Thanks for your interest in the videos. All right, we're going to go ahead and get started again here. With the final leg of the workshop, we've talked about, why it's important to track load results from our projects. We've gotten a detailed tour of the new PLET model from EPA and from Tetra Tech. We've looked at all the methods that are kind of under the hood, the parameters associated with them, and resources for getting those parameter values. And so now we're actually going to use some of those resources and use them to generate area-specific parameter values to enter into a PLET project for an example proposed treatment wetland. But before we jump right into that, I want to take a moment to talk about a couple best practices. And, I speak only for myself here, but one of the things that we've talked about a couple times this morning is when you start a PLET project, you have to enter in a HUC 12, and it pre-populates that project with average parameters for that HUC 12. And so, practitioners stretched for time might have they might feel a temptation to say, well, those are average representative parameter values for this HUC 12. I'll just use those for my project area. And I'm going to go out on a limb and say that I would consider that to be very poor practice, and I would say that you would not be able to have much confidence at all in the accuracy of your model, regardless of what model you use. And so, to think about this, it's helpful to kind of think about this in terms of GIS land, right? So the data that we have to parameterize these models, it's spatial data. It exists in polygons or raster format that we can make polygons that are basically irregular shapes on the surface of the earth that are partially overlapping each other. And when we start to put all these parameters together to estimate amount of erosion or amount of runoff, it becomes very important the way that these components, be it land use, soil type, and topography, how they line up, right? And so we're going to do an intersect between our land use and our soil types later. And this is what it looks like for this property here. And I just want to show you this because there's a ton of little polygons here, right? And one could go even further. They could dissect the area into areas of kind of homogeneous slope, right? And that could be a third polygon that you would intersect here and get even more tiny little slivers. And in a perfect world, we would build a watershed in PLET, a area of analysis for every single one of those little tiny polygons. Now, that's not practical, and it frankly is not merited given the kind of simple methods associated with the PLET model. And so we're not going to do that here for our example, but the point here is that you could have, this little tiny polygon right here could have a really high slope, and it could be an agricultural field that gets tilled twice a year, and it could have highly erodible soils, and it could pump out a hugely disproportionate amount of the load for the whole area. Whereas you could have a really large area here that's perfectly flat, it's forested, it's got low erodible soils, and it produces almost nothing. And so location matters. And that is why it is not advisable to just accept, average parameters for a much larger area than what you're working on. And so, I have two best practices that, again, this is only me speaking here. My advice for people trying to create load reduction estimates for your BMP projects is one, model it at the site scale. And two, if you have a larger site, you might want to consider, so a large site that's heterogeneous with respect to land cover, topography, and soils, you might want to consider, how much extra effort would go into it to subdivide it into a couple smaller areas of analysis that are more homogeneous with respect to land use, topography, and soils. And so I'll leave that there. For our workflow, we're going to be looking at a 20-acre area that is going to drain directly into a proposed wetland. And so we're just, the whole area is going to be serviced by the BMP. We're going to keep it simple. We're going to come up with area weighted averages on a per land use basis. And so let me pull up the PLET here one more time. And so recall that our universal soil loss equation parameters can go in on a per land use basis, right? And so we're basically just going to have one watershed. We're going to try to put unique K and L factors for each of these. You should put unique C factors in there too. I think, PLET does put varying C factors. So I'll back up. And so when you preload this and it just gives you your Huck 12 average parameters, all the K and the L's are going to be the same for all the land uses. That's not true for the C's. The C values will give you a value that's appropriate for that land use. And you might decide that you want to accept that C value. We have lots of resources up on the web page for you to come up with local C values that are going to be good. And also we'll come up with appropriate parameters for the curve number portion as well. So here is the basic workflow. We've got 4 sets of data, right? We have an LS raster. We're going to create that with our tool that we looked at earlier. We need to come up with a project area. We need a land cover data set. We need soils. And we're going to use kind of a zonal statistics to give us average LS values for each land cover. and that's going to be automatically put out with that tool. Now for we can, maybe digitize or clip out a land cover to our project area. I just have one, right? Because no one wants to sit here and watch me digitize land use. So we've got our land cover data set, and we're going to use that land cover data set and the soils data set that we have gotten through the query that was provided by NRCS. We're going to intersect them, and we're going to get what I showed you here, which is lots of little polygons that are unique to a given land use and soil combination. And then we're going to pull all this into a spreadsheet, and we're going to do a few manipulations to get area weighted average values for K and for LS, and also our hydrologic soil group. And then we're gonna throw it into PLET. So with that, I'm going to go ahead and pull up this. So you guys have access to all this GIS data. I have it all pulled in here. I've got a few extra things just to introduce the site. This is the workshop's resource webpage. And this resources page just has two things. It has a list of links, and it has a list of downloadable resources. We'll be using the LS factor calculator tool. We'll be using the data that's zipped up here. And this spreadsheet is basically what I'm going to be doing already populated. So you can kind of just click on it and be like, whoa, Adam's typing equations way too fast. Well, just click on your version of the spreadsheet. You can see what I typed in, and you can keep that as a reference. And I'm just going to be kind of deleting things out of this spreadsheet and redoing it in front of you in real time. So this is a roughly 20-acre area that's draining to a wetland, right? So this particular wetland is actually a 3-celled system. One or two of them flow into another. So if we wanted to, we could use the BMP calculator in PLET, and we could do in-series simulations of these. To keep it simple here, we're just going to assume we've got one wetland at the bottom here, and we need to come up with a load for it. So the first thing we need is a project area, right? So it's a watershed here, a drainage area, but it could just as easily be a whole property, right? If we want to know, this property, this whole farm area produces this much load, and I want to know if we do all these BMPs, how much is that load going to be reduced? So it doesn't necessarily have to drain in the same direction to use the PLET model. In this case, it does. So I hand digitized this drainage area here. I'm not going to go into how to hand digitize a drainage area from contours, but certainly if that's something new to anyone, I'm sure there's plenty of YouTube videos and resources online if you digitize, or if you Google digitize watershed with elevation contours. So the next thing we need is land cover. And I had mentioned earlier that the national scale data sometimes is not going to be appropriate when you get down to a large scale, small area like this. And this is a good example. So I have here, this is the national land cover data set. And you can see here that the data is very coarse with respect to the size of this area. But more importantly, if we just look at what's there, most of this area is designated as developed open space. And there is some lawn here, but it's mostly hay fields, some forest, some ag fields, some row crop there. And I'm not seeing that there is a good correspondence at all with this data and what's actually on the ground. And so it's a small area. So why not just take the time to digitize it myself. And then I get land use categories that are going to be, appropriate to PLET, right? Make my life easy. And so I went ahead and I digitized this. We've got hay fields and pasture and in a row crop fields here. I've got some open space and green, and we've got this one area of farmstead, which we're modeling as an urban BMP. And so the first thing that we want to do is, in PLET, we just need to know the actual areas of each land use, right? And that goes right up top here. We have one watershed. I never renamed this from the HUC 12, and it's too late now. You actually can't rename these after the fact. And I already entered this data in. And so where did that data come from? Well, I hand digitized, within this watershed. And if we open the attribute table here, I have this acres column. And all we got to do, let me just sort this. All we got to do is select everything in that table, right click over here on the gray area, and then copy selected area. And so we're going to bring that into our spreadsheet. And you can see I've already done this here, but I'm just going to do it again. Now, the first thing I want to do here is kind of get rid of some of this data pollution, just to make it a little easier on my eyes here. So you can see that, these are the same numbers that are up here. And PLET, it wants acres to 2 digits. So I'll go ahead and I'm just going to make all of these cells show 2 digits behind the decimal point. And so basically so cultivated cropland, we can just go into our PLET here, cropland, double click, and the answer is 2.56. Okay, we go back, and for pasture, I'll use grassland hay, for example. So I have this category of grassland hay that's 5.48. PLET doesn't have grassland hay, right? But they do have this user-defined one. So I come in here and I put 5.48. And what's really important for me to do at this point is come down here and update my curve number values for that user defined. And so I talked about that earlier. I got those straight out of that TR55 tables. I showed you exactly where it was in the table, and I have that saved here. So this is the information for meadows, which is what we're going to use to describe our hay fields. And so 30, 58, 71, 78. I actually think this isn't updated here. No, it is. So 30, 58, 71, 78. So I just hand entered this right here. We'll also note that I have something that I called farmstead here. And that is, this area right here where we've just got, some farm buildings, some gravel roads, and all that is exactly what that description of farmstead was in the TR55 table, if you recall that earlier today. And so, here's the values from that table. I entered that into the PLET. Now, I had to because that's not an option here. We've got transportation, multifamily, single family, all of these options, but we don't have a farmstead option. And so what I got to do is I got to pick one of these that we're not using. Now, there's only 2 that we are using. We're using farmstead and developed open space. Those are our 2 urban categories. And so we've got 20.3% farmstead, and we've got 79.7% open space. And I'll go through calculating all that real quick in a moment. That's not super sophisticated spreadsheet work, but we'll go through it. But I enter that here and I put it under multifamily. Why multifamily? Well, it doesn't really matter. Basically, I picked one that I thought would have a similar amount of impervious surface as the farmstead. Now, really, there is going to be a runoff concentration that's associated with multifamily, right? So you just need to understand that there's not a runoff concentration tailored to farmstead. And so we're applying that multifamily to farmstead. Is that a best fit? Probably not. I'm open to folks wanting to make arguments that, institutional or single family might be better. But this is the choice I made. We're limited to these 10 urban land uses here. So unfortunately, you can't change the name multifamily, but you can go ahead and update the information up here. You actually can change the name here if you try, but it won't save. I've tried it many times. So you just have to remember multifamily is now farmstead. And so that's where all this information is going into the spreadsheet. And so, real quick, I calculated, we'll get the total here. So total is equal to the sum of all of these. And again, you can just kind of click on everything I've done in the past to get the equations. And we don't really need these percentages for all of our non-urban land uses. We only need the percentage for our urban land uses. So I'm just going to skip the percentages and I'm going to come over here and I'm going to steal these headers. And here I want to know the total area, the sum of our urban components. And so we've got 1.11 acres of urban. And so I'll go ahead and just merge this to make it look a little nicer. And we need to know the percent of urban area that constitutes farmstead and developed open space. So we're just going to say farmstead divided by the total urban area. And I'm going to stick a little $sign in here before the 20, and that's just going to let me kind of drag this down in keeping the denominator the same. So here are our answers. They should look familiar. 20.3 and 79.7 are the values that we entered down here for the urban land use breakdown. So everything's 0 except for multifamily, which is farmstead, and open space, which is open space. So that's all there is to it for the land use side. So our next task is to get our soils data. And we need to get that soils data on a land use basis. And so recall from our workflow here that is going to involve getting an intersection of the soil and the land cover. And so we'll do that. And, a basic intersect tool is certainly, it's the exact same in ArcPro. And they have an intersect tool called Intersect in QGIS. They surely have many with all the automatic plugins there as well. So intersect. And, this speaks a million words, right? It is all the polygons that result from intersecting these different data sets. So we are going to throw in our land use data and our soils data, but I forgot a step. Okay, So we have soils data here, and this is the Surgo data. This is a shape file. You know, I just exported the geodatabase as a shape file just to make it easier to throw up with the examples. But the process is the exact same. I need to join the data that resulted from that query. So this is the exact data that came from that query. A browser table popped up. I copied it. I pasted it in a Excel file, and that Excel file is, in that zipped folder that you could have downloaded. An important point for ARC, for old school ArcGIS 10 point whatever that I'm using here. I don't know if this is true of Pro anymore, but when you do this, you have to have an XLS file, right? The new XLSX files don't pair well with ArcMap. So you just need to save that after your query. When you paste it in Excel, save it as an XLS file. And so this is the only sheet in there, and I click add. And this is a great opportunity because they showed using Pro that they linked these with MU key as the primary key. But if I pick MU key, I don't have one to point to in my Excel file. And that's because the MU key is stored in Surgo as a string, right, as a text field. But when ArcMap reads my Excel file, it sees that the MU key is all numeric, and it just immediately calls it numeric. And so you'll note it in Steve's slide, when he did this with Pro, he checked this box that said, make this field a string. There is no way that I'm aware of to do that in ArcMap. So you could do some fancy stuff by, adding a letter to all of the MU keys in your Excel file, and then adding one in QGIS, and that'll solve the problem. But we have this MU symbol, which is what most of us are used to as the soil types. It's the letters that describe which soil it is. And those are unique for a soil area, a soil survey area. So as long as you don't have 2 counties worth of data in here, you can link it up with the MU symbol. And so that's what I'm going to do here. We'll press go. And if we look at our attribute table, we now have all this data, right? It used to stop here at MU key, and everything from here on was just joined from that Excel table. And this is a little more than we actually want. All we really want is our hydrologic soil groups and our K factor here. You'll notice that there's a few things that don't have values for them. They're very few and far between. There are things like ponds and things that are just not going to have K factors, even if you look way back to your old paper soil survey. And so in those cases, you'll just have to make some assumptions. But with that, I'm going to go ahead and do that intersect now. I'm going to drag in our land use, and we're going to drag in our soils data. And I'm going to save this. I've got this processed data folder here for my example. So I need a name, and we'll just call it LULC for land use land cover _ soils dot shape. There's way more attributes than I want to deal with here. I don't have power to remove too many of them with this tool, but I'll go ahead and say no FID fields just to reduce it a little bit. but you can just accept all the defaults here, run it, and this should take very little time with this small area. And what we've got here is our attribute table with both the land use and the soils data. Now, the important step that's easy to forget about that you can't forget here is that this tabular data has not changed since the geometry has changed. So our acres is not up to date. So we have to physically change this before we can use this data. So I'm going to go in here, I'm going to right click on acres. I'm going to calculate the geometry. And as you can see, all those immediately updated. So I think we're ready to bring this into to our spreadsheet for processing. I have this land use, land cover table here where I've already done this. I'm just gonna kind of move over here and add this stuff up here and do it all again. Copy. Paste. Okay, so the first thing I'm going to do is get rid of some of the data pollution again. We definitely want our land use. We definitely need our acres. So I'll delete those. And the only other things we really need are our hydraulic soil units. Are we still there? Looks like we're running. Can folks hear me?
We can still hear you. We lost your screen share though.
Yeah, I got kicked out for a brief moment there. Let me make sure that the let's see if the recording's still going. It looks like we're still recording. Okay, that's good. Sorry about that. I'll just pick up where I left off. Okay, so I was just getting rid of the rows that I don't need from this land cover and soils data set here. So I'll delete these. This sort column is something that I added to my land use data simply because, first of all, you need to sort your land use here. Sort this table by land use because it's really going to help visualize some of the things that we're about to do, as you'll see. There's a certain way I like this stuff to be sorted, so I added that sort layer. Okay. And I'll go ahead and just move, well, no, I'll leave it there. Want to keep this looking like the original table just to make sure that I don't make any mistakes here. All right, so a recap on what this is after we did the intersect. Each one of these rows represents a polygon that is unique and homogeneous with respect to a land use type and a soil type. Now, that intersect tool allowed for multi-part features, and that's important. And it's something that, if you're using another tool in QGIS or something, you might want to keep track of. And so what do I mean by that? I mean, if you have two different polygons that are both forest and both, soil type A, then it's going to be included in the same piece here. And so immediately I click this one and I get an example where we have two polygons. And that's great. That simplifies our life. We want to analyze those together. And so since they're combined, we know that the acreage here is inclusive of all such areas. So that just keeps things cleaner for us. So what we're going to do is two different things. Recall in PLET that for our hydrologic soil group, we only have one that we get to pick for the whole watershed. But for our K factor, we get one for each land use. So we're going to come up with one area weighted average hydraulic soil group for the whole watershed. And then we're going to come up with separate area weighted average K factors for the whole watershed. And so you might say, Adam, how can you average letters? And so that's a good question. And, they're letters, but they're ordinal letters. And so we can simply create these or transfer these into numeric. So the way I do it is we've got letters A, B, C, and D, and those are going to correspond to 1, 2, 3, and 4. So I'll create this new column and I'll call it hydraulic soil group num for numeric. And I'm going to put in an if statement here. But you could just manually go down here and enter a 4 for every D and a 2 for every B. I'm going to say if this cell, well, I forgot my parentheses. If open parentheses, this cell equals B, then it's 2, comma, if this cell equals C, then it's 3. And if this cell equals, I'm on 4, or I'm on D, then it's 4. And if that's not true, we'll just have it report some flag. I'll say false. And we'll close out all the parentheses. And hopefully that worked. All right, great. So it worked. So we've got a 4 for the D. And if we click on this cell, I can just click on that little box, that little square in the bottom corner. I just double click on it and it'll fall down. Okay. And so what I want is just basically the average of all of these weighted by the acres. And so I'm going to create what is called a hydraulic soil group weight. And that's going to be the proportion of the acres of this one polygon for the whole area. So what I'm going to need first is I'm going to need the total area, right? So I just come down here under my acres and I say equals sum. And I just grab all of these values and that's my total. My total is 22.48 acres. So the proportion of that is represented by this row is equal to these acres divided by the total. And again, I'll stick my $sign in here in front of 26 so that when I click this down, this red cell stays there so that it doesn't move down the way the blue cell is going to do. So again, double click on the corner. It dropped down. That didn't work. It's because for some reason I didn't get that $sign in there. All right, let's try it again. So that's our hydraulic soil group weight. So now we'll come up with a weighted hydraulic soil group. And that's going to be the numeric hydraulic equals the numeric hydraulic soil group times the weight. And we drop that down. And the sum of all of these is going to equal our weighted average. So equals sum, drag it down, and we get 3.51. So unfortunately, it's right in the middle of C and D, but we'll just follow the normal conventions of rounding, and we'll round it up to 4, and we'll say that D is our weighted average hydraulic soil group. So then we can go into PLET up here, and we can say D, and so you double click it, and you get a drop down, you select D. Okay. Now we need to get our K factors on a land use basis. And it's going to follow a very similar workflow where we're first going to do our K weights. No, that's not true. The first thing we're going to do is we're going to get the area for a given land use, right? So we need to sum the rows that are associated with a given land use. And then we'll create a weight that is the proportion of this polygon for that whole land use. And then we'll do a similar operation that we just did. So we'll say LULC acres. And the function that we're going to use here is called the sum if function. So equals sum if. And what we do here is we click the land use row, and we're saying if an item in the land use row is equal to, and then we select it again, an item in the land use row. So we're basically saying for all the same items within this row, we're going to sum, which is the third argument, our acres here. And we click this, and it wants this @ sign. That's new. I just ignore it and press OK every time, and it finishes it for me. So if I go ahead and drop this down, what I'm going to note is that we have the same number here repeated for the same land use. All of pasture has the same number. All of grassland has the same number, and so on. So these are the totals for those. So we can now come up with our K weight, which is going to be the proportion of the area within that whole land use unit. So that equals our acres over total land use acres. And we don't need a $sign here because we've got the correct item going all the way down. So we'll just let it drop. And we've got our K weight here. And so now what we need to do is get a weight id K by multiplying our K value, which is here, times the K weight. So we drop this down here, and now we need to sum all of these weighted K values by the total of that given land use. So we're going to do that again with that sum if function. So we're going to say this is our weighted average K. And that's going to be equal to sum if the land use equals the land use, then we're going to sum our weighted Ks. And again, we'll get the same number repeated for a given land use. So all the pastures have the same K value. So they're repeated a bunch of times. What we need is a convenient way to just get a list of one K value for each land use. And a real convenient way to do that is with this function that I think is relatively new, which is called unique. So equals unique. And then I just select this whole column, press enter, and it selects everything, right? So I didn't even pick a header because the header is unique. So we got all of those. And if I just do the same thing over here, equals unique for our weighted average K values, we'll get them. And I don't know why it gives me zeros at the bottom, but they don't hurt anything. So we'll let them be. And so now we can enter this into PLET. And so let's pick a number of digits that we want to enter into. And so I think PLET offers us like 5 digits, which seems a bit overkill to me. Maybe we'll go up to 3 here. And so our cultivated crop K value is 0.49. So we go into PLET for cropland, K value 0.49. And we repeat this for all of these land uses, right? We can do our grassland is 0.286. So we come over here to user defined 0.286, and you get the picture. We do that for each of them. And so the last thing that we need here is an LS factor. Okay. And so that's where we're going to use our tool. So I have this tool right here. I'm just going to do this in an ARC catalog. We don't need ArcMap for this. And I'm going to open up the tool and we're going to see what it wants. Now, the first thing to enter here is workspace. I'm going to warn you guys, it's a little fickle. You need to enter the workspace first. If you don't, sometimes it'll keep throwing up a pop-up saying, what's your workspace? If you like add, say, the project area first. And it's crashed ARC catalog for me several times doing that. So just save yourself some trouble and put the workspace in first. So I'm going to find my workspace here, which is right here. I'm just going to click on it in our catalog and then copy and paste it up here. Now, in the example data, this is the exact folder that's up there. I've got this 2.5 meter DEM. So this is an OSIP DEM. That's 2.5 feet. Sorry, I think I said meter. It's in state plane. Notice I have 2 LS tools here. I got one for feet and one for meter. I got a slicker kind of Python tool that'll do all that for you. I'm not quite comfortable releasing that yet, but that might be something. I'm considering another workshop that's kind of focused on LS, if there's any interest in that. And so that might be something that I can provide in the future. But this time, you just have to use the correct tool. If your DEM's in feet, use this. If it's in meters, use this. Another really important thing to mention is that your vertical units have to be the same as your horizontal. That is assumed. If you have a DEM that, you know, a raster cell is a foot on the side, but your vertical measurements are in measuring elevation in inches, you're going to get the wrong answer here. All right, and that is spelled out over here. I've made all those disclaimers. So if you're going to use this tool, read this, please. You know, the workaround is simply to go in and edit your DEM and change your vertical units. So I'm gonna drag in my raster, my DEM right here. And then the next thing you got is this expression. And so I'm going to remind you that the universal soil loss equation is for estimating soil erosion from sheet and rill erosion. It is not for estimating concentrated flow erosion. And so when you create LS factors across an entire raster, you can get really long slope length factors occurring there as a result. And so what this does is one of the intermediate data sets created with this tool is a flow accumulation. And this is saying, it's looking at that flow accumulation and saying, how many cells does it take to constitute a concentrated flow path? And then it basically creates a stream network on top of all of those cells, and it turns them all null. It makes them no data, so they don't influence the calculation of the LS factor. Again, this is something that, you know, I could have made this happen automatically or made it report in acres if we just you know, pass out that Python tool. That might happen in the future, but I wanted to give you all something to use right now, because frankly there's not a lot of resources. I will echo what I mentioned in the chat when Elizabeth was asking these questions about QGIS. There's a Saga plugin tool set that's automatically loaded with QGIS, and they have LS tools. But there are no LS tools that I'm aware of for ArcGIS, Pro or otherwise. And, you know, I've had trouble getting those Saga tools to work in QGIS. I have not tried using the Saga, you know, interface itself, but I thought all of that is a little too complicated for this one day webinar. So I've provided this. Now, so what are you going to enter in here? What in the world how do you figure this out? And so we got to come up with a rule for what area constitutes a concentrated flow path. And so I have here a recommendation based on the Russell document, that Agricultural Manual 703. And it says that slope lengths are generally less than 200 feet, meaning that after 200 feet, you might expect concentrated flow to ensue. And I talked to Steve Baker about this to just get his gestalt, and he said, yeah, in my opinion, around here, it's more of a maximum of 100 to 200 feet. And so this 200 is a maximum, right? You wouldn't want to use necessarily more than that. You might want to use less. And so the way I envision this, because we got to take that slope length and turn it into an area. And I'm picturing a semicircle with a radius of 200 feet, right? And so the center of that circle is where concentrated flow begins. And we got a watershed, you know, that's shaped like a half a circle. And so if we calculate the area of a semicircle that is 200 feet, and we can go to our spreadsheet, go to LS, and we can do that. And so it's 1/2 pi r squared, right? And r in this case is that 200 feet. So 1/2 pi times 200 feet squared. And that gives us the number of square feet that we are going to say will create concentrated flow. And then we divide that by the area within a cell, right? So our cell size is 2.5 feet. 2.5 squared is 6.25. So I divide this area, that is the threshold area, by the area of the cells, and we get that it takes 10,053 cells to be the threshold value to create concentrated flow. And so we're going to enter that here. I gave you, that same example right here. So here's what we're going to use. Value, right? And so that's the value of that raster, that the cell accumulation raster that we're going to have in here is greater than or equal to, right? Because if that much flow accumulation happens in the cell or more, we want to not consider that for our slope length factor. So equals 10,053 cells. And then finally, we need a project area. Now you could just put in the whole project area here that's not subdivided. And if you put in an unsubdivided polygon here, you're going to get a table that tells you the average slope length factor for that area. But if we put in the land use data set here, what's happening here is we're doing a zonal statistics function on our resulting LS raster. And we're going to say that the zones that we're interested in are our land use classes. And what this is going to give us is the area weighted average LS value for each land use. And so you got to click this checkbox. I wish I could have just made this checkbox go away. I didn't know how, but you have to always click it. It says it over here in the description. And if you don't click it, basically it's going to calculate these values for a rectangle around the project area. So you'll be incorporating areas outside your project area, and therefore the table outputs are going to be wrong. So you have to check the box, all right? And so I click OK, and this happens pretty quickly, and it's done. So I go to the working directory that I gave it, which is process data. I'm going to refresh it, look in here, and I've got, I want to make sure this is the right folder. It is. And so I've got, we can preview it. This is my raster data set. You see these bright white line down the middle? That's no data, right? Those are null because those were constituted concentrated flow paths. And we've got, oh, that's the wrong folder. And we've got this table here. And so this table has land uses, and it has our mean LS value. So this is the information that we want to get into Excel. So I don't think I can copy and paste in Art Catalog. So what I'm going to do is I'm just going to drag this table into ArcMap here. Right click, open the table. Highlight all the rows, right click. Then we're going to bring it into our Excel file. And you can see I've already done that here. Just paste it in, get rid of our unwanted rows, unwanted data here. And that's it. So we can see correspondence up there. I'll give this, I'll say that we want this data at to 3 decimal places, just like K value. And you can see it's the same. 0.356 for this is actually our farmstead, which we don't really need, right? We only need non-urban land uses for this. So for forest, our LS factor is going to be 3.781. And I just want to take a minute to point out how different these values are, right? We've got a 0.3 for cultivated crop, and we've got a 3.8 for forest. Now, recall that the revised universal soil loss equation, all of the universal soil loss equations are simply multiply the factors, right? So it's K times C times P times LS. And so if you multiplied the whole thing by 0.3, and then you multiplied the whole thing by 3, you are going to get very, very different total amounts of erosion, right? So the LS factor is commonly considered to be the most sensitive parameter of the universal soil loss equation, simply because it can get so high. And so I think there was a question earlier in the day about sensitivity in PLET, and I'd say LS is a big source of sensitivity, which is why we're spending so much time on it here. So, forest 3.781, go into PLET, find our forest LS 3.781, and on and on. So that's basically it, right? I mean, obviously there's other things that we need to enter here that Aileen went over this morning. You need to know something about the livestock in your watershed. And I got this information by talking to the landowner, right? And so some of this data just requires a lot of work. You need to know something about septic systems, right? And that data is often hard to come by. You typically have to reach out to the health department for that. It turns out that there's not a septic system on this property. We're accepting the default nutrient concentrations. I've already showed that I've updated some curve number factors for my specific land use needs. We're going to accept the default land use nutrient concentrations in runoff. We do not have any irrigation. We're not going to be considering wildlife. So that's it. That's everything there is to input. And so what's left is just to create our BMP. And so for that, I bring you back to the transition right before we left on part 3 of the workshop, which is we need to create a custom BMP, and these values came from this resource, the Stormwater Retrofit Practices Manual 3, gave us these median efficiency values for stormwater wetlands. And Chris also gave us a great resource that he threw the link in the chat. I will be adding that link up to the resources page after we finish here as well. So let's do it. Let's go into BMPs. And I've already done it, but we'll walk through it again. And so basically, we're going to create a user-defined BMP, and we might call it treatment wetland. And our in-value efficiency is 0.25. For P, it's 0.5. We don't have any data for BOD, so we're not going to attempt to act like we know what we're talking about. We're just going to leave it blank and not estimate reductions there. And the efficiency for sediment was 0.7. And so I'm gonna delete all this and not save it because I've saved this many times, and I wish I had a chance to ask Eileen, but I can't figure out how to delete a user-defined BMP after you create one. But so you create it, and nothing populates down here right away. You gotta add a BMP, and once you add a BMP, you get to select from the drop-down. And so the user-defined stuff that you've added just finds its way into this drop-down. And so you're just going to click wetland, and then it's automatically going to have all these values for it. So you'll do this 4 times, right? Because in PLET, you get 1 BMP per land use, unless you use the BMP calculator and string them together through that. But even the BMP calculator is limited to 1 land use at a time. And so my entire drainage area for all these different land uses is all going to this one wetland. And so I'm just going to create a BMP for each of my land uses. And I'm going to say that 100% of those are being applied to the wetland. So we add a BMP, we select pasture, we select our custom BMP, it populates all this, and then we have to come in here and type 100% of that land cover goes there. Unless that's not the case, and you have a larger watershed and this BMP only services a portion of it, then that number might change. So we've got this applied to 100% of pasture, cropland, forest, and our hay fields. But we also have a small amount of the area that is in urban. That's the pink, and that's kind of this bright green color, which is developed open space. And so that's also going to the wetlands. And so for that, we're going to use the Urban BMPs tool. I'm going to go ahead and reset all BMPs, Urban BMPs there, because I've already added it. And so we'll do this from scratch. We have two types of urban land use. We have farmstead, which fit inside the multifamily bucket. And so we can come down here and there is a wetland detention option right here. So we're going to select that. And right up here, it says, this is the total amount of acres in that land use that you can use. And since all of our land uses are going to the wetland, we're just going to type that number 0.22533. And we're going to apply it. And so that was added down here. We can see we have for multifamily, this BMP is in effect, but we still need to add it for our open space. So go up here, click on open space, select wetland detention, and we're going to click or select the entire area, which it says is 0.88467. Apply. And we come down here and we can see that now 100% of both the farmstead and the open space are being applied to urban BMPs. So that's it. We have created our model and we can look at the outputs, but don't anyone hop off the line yet, because there's a real important thing that I want to point out that affects the way that we might choose to model this when we create user-defined BMPs. So if you look at our outputs here, we have these percent reductions over here. And our percent sediment reduction note is 70%. That is exactly what we would expect it to be because we put in an efficiency of 0.7, right? But we have this BOD reduction and we had a 0 there. We had 50% for P and we're getting 68%. We had 25% for N, we're getting 61. So what's going on here? And the answer is, if we go back to our what's happening under the hood in PLET, we can see that our sediment loads are feeding back into BOD, phosphorus, and nitrogen. So when I put in this efficiency value right here, this is the efficiency of what's associated with the runoff only. It does not include anything associated with the sediment. Recall I made this distinction in the last session where I said everything in PLET is kind of divided in two buckets. It's the runoff where we have these land use based concentrations, where we've got, per animal concentrations, and we can multiply that by the runoff. And then we've got our sediment that's coming from the universal soil loss equation, and it's being delivered via a sediment delivery ratio. And so the critical question that you got to ask yourself at this point is, where did these efficiency factors come from? And did they lump the soil, the sediment-derived nutrients, or did they just measure, the runoff coming out as water, and they didn't look at the sediment constituents? I'd like to hope they looked at the sediment, right? If they're reporting this as a total BMP efficiency, then it really should have included the sediment. But the truth of the matter is we don't know the answer to that. That information is not supplied anywhere in the documentation. And so the way that I did this for my H2 Ohio application is that I just decided to be conservative about this. And I said, I'm not even going to use this BMP portion of PLET. I'm just going to calculate my loads going to the wetland, and I'm just going to subtract 25% from nitrogen, 50% from P, and 70% from sediment. And that's what I'm going to report. So, for everything that's in PLET already preloaded, definitely, you're using PLET, we're using their methods. So, I would recommend reporting their methods. But if you're using your own efficiency values, you have to know what they mean. And if you don't, I would say to err on the side of being conservative. With that, I think that is all I have. And we'll open it up for some questions. We finished early. I'm really proud of myself. I know that's a ton of information, maybe information overkill. I'm incapable of giving presentations online and monitoring a chat simultaneously. So I'm gonna look in here for the first time in a while and see what I missed. Must ask, how long did it take you to develop this unique land use PLET model the first time? It looks like a significant time commitment to do custom models. Well, I'll say it takes a significant amount of time to come up with the method if you've never done this before. But how long does it take to build the model? Well, I just did it. And I just did it in basically, we started back here at, I'll say 2:45, I started doing this. So it's been less than an hour. Now, what you didn't see is me sending a bunch of emails to Gorman Heritage Farm, trying to find out how many livestock they have, and all of those things. So, it's like anything, there's a learning curve, but you figure out what you need to do. And once you have your workflow, and hopefully you all have your workflow now, you have this spreadsheet, you can just take it and copy exactly what I just did for your models. And so, yeah, you got to take the time to dig into your C values and make sure that you have appropriate C values and all that. But, I would stress once again, if this is, do we really need to do this? Can we just accept the Huck 12 averages? I would give, an absolute no on that. And, I had to cut this out of the presentation for time, but I wanted to show an analysis where I did this model at the Huck 12 scale, and then I averaged it, for the whole property. And then I did another one when I averaged it for just the drainage area. And the variation in those estimates were 2.5x, right? So big differences, but it's not like I went and I found the best example of that, right? This is just what I used because I just you know, I just built this model for a funding application. So it could be really bad if you used Huck 12 scale parameters and assume that that is representative of a 10-acre field somewhere. Particularly this one, this is in the Sharon Creek, Mill Creek watershed. It's urban and it's the only ag field in the entire area. So there's that. Any other questions? Looks like Jeff Glanville gave some real helpful background history on some things that folks should check out in the chat. To summarize the basic history of soil survey, we basically had teams of 3 to 5 people in each county for about 5 years using hand tools and/or hydraulic truck-mounted soil probes. Major field work done from the 40s through the 90s. We walked over every part of each county, lab data for greater than 3,000 sites. In Ohio, close correlation between counties and adjacent states with personnel from USDA, ODNR, ODA, OSU. Man, that sounds intensive. Maps digitized mainly during the 20s to 2010s. Current soil survey staff are working on data gaps and consistency across the country and state lines. So that's good information. Understanding the data that we're using, as I hope has been demonstrated a few times today, is really important.